and we're going to let András and László talk about their work on the generic resource manager.
Okay, so basically the idea was that we're coming from a different angle. We're not working only on a single application, but we try to come up with an application layer. So try to save up time for the applications. Basically what we're trying to do is that the idea is to support multiple applications with our layer, and it means if our application layer becomes efficient enough, the applications themselves do not need to be new ever and working on many other optimizations they do if we can put it into our layer.
Just to mention that most of our application is currently, they are not DPDK applications. They don't know anything about DPDK. It's just that we want them to configure their application model, and basically that's how we can gain transparent NUMA awareness, and we will describe that.
In the last year, in our presentation, we had a couple ideas we did not implement. We just had them in mind, and basically the generic resource manager was already there, and we're still not yet ready with that, but we have an idea and we have many portions ready. And there are actually a couple others which are already being implemented. So the resource, in our terms, we don't really need to explain them. This was just an idea if we had much time for the presentation, but we don't. So basically the resource is, as we think, is that any physical or virtual component of limited availability. That's what's important for us. And if you take a look to the typical resources in the DPDK, by the CPU memory, even the virtual addresses, packet pools, whatever, we take all of them as resources, and we're trying to classify them. So, as we wanted to support multiple applications, we needed to have a better control over all of these resources, and we tried to hide the real environment from the application, because we think that if we show them something we think will be much more efficient, than in that case the application can work much more efficiently. We also have some sort of migration support, but this is not the live migration we had the discussion about yesterday. What we're talking about, or we're thinking about as migration, is that if you have an application in a VM and you want to make it start in a complete other environment, even with different number of cores, different amount of memory, and different type of interfaces, basically right now we can do that, because what we provide to the applications is our service layer, and we have some sort of environment detection there also. I'll talk about it later. And basically all of the resources we had there. We had one more important thing, access control. So we also came up with an idea that we can save the applications from their own faults if some process overrides accidentally the other process's memory area, and also we have access control over interfaces and basically any other resources.
And it also means that the application, so if in the config an application, you have multiple application instances and different types, and if one type you don't want to allow to access that particular memory, they cannot even attach to that memory partition. If you are dealing with memory, so we can restrict that.
Basically the resource pools are just generic terms. On any level of the resources we can have the resource pools. The example is that we can have a server, and on the server we can run compute nodes, and within compute nodes we can have virtual machines, and within that we can have DPDK domains or just applications. And even if you want, you can add much more levels even between them. So for instance, we're having a CPU or a CPU pool, And the CPU pool basically contains, or might contain, lots of CPUs. This is basically what our original or stub resource is. And we put this type of resource to a bucket, and on the very same bucket we can have other types of resources. Here we're mentioning just the memory type and the interface or port or queue or whatever you want to name it. And basically what we do is just, we do subsets of these resources for the lower level. So if we're on a server level and we go down to the compute node, then we're going these buckets for the compute nodes also. It doesn't need to be all the resource types within the buckets, so we can just assign them as we want. And it means that on the lower level we have just a fewer amount of the original resources, so a couple of CPUs just out of the 36 in the previous one, or 8 of the previous 36. And the idea is that we're adding attributes to these resources. So in a real-time system, or when you want to work on optimization, there are a couple of interesting things for you regarding the CPU. Namely, if it's an HT pair, so if they are siblings, or they are on a given socket. We're storing all this information, and we're using it when classifying and we're assigning.
So this is just the same thing what usually the VM manager does now, or the operating system does. It keeps track of resources. It's just that we want to get detached from that environment, because you may be running different types of hypervisors, different types of operating systems, whatever, where these resources are handled differently. So in this way, depending on the environment where we're running, for example, if you're running on BSD, then you collect the resources in a different way than in a Linux machine. And that's what the EAR different EAL does today. We have Linux and BSD layer in EAL. Yeah. And so the same thing with the hypervisors. If you're running in a VM, like in a Xen virtual machine, where you don't have any NUMA information, because it doesn't yet support exposing NUMA, and in that case, we can just somehow get the information, like by detecting the NUMA topology, or just talking with a hypervisor layer, and then fill up our databases, and then we can attach these attributes to our CPUs or our resources.
So these resource pools can be multi-level, and we can go down and down and down deeper. And also regarding the information we need to, or we would like to pass to the guest about the architecture itself, this resource manager can be a multi-level one. And if you come up with an idea how to communicate between the levels, they can share the appropriate information. So in case of the smaller or more details, more level down resources, we just have fewer CPUs or fewer interfaces, or even more, and still keep all those attributes. There's an example. This is a really simple one. We actually came up with a pretty complex configuration file. We have lots of options to configure, because the idea is still that we would like to configure our layer to make the application on top of us work efficiently. And it means that the optimization job, which in other cases are done on the application side, sort of comes to our layer. It means that we need a smart resource manager and a smart configuration. So basically, if we would like to appropriately configure an application, it means that it takes time. So we come up with an idea how to share the resources, how to assign them, but it means you need to do it only once, and it's still faster than optimizing the whole code of the application. And the other benefit is that with just a single change of a line in the configuration line, you can reconfigure basically the whole application. So it means that you can configure it to another memory using another packet pool, using another interface.
Which is useful when you're running in different environments or different platforms. Then you just change the configuration, and you can get a lower memory footprint, or you can get NUMA awareness or things like that, just by changing knobs in a config.
So if in a basic configuration file, we have the CPU aliases, let's call this alias as foreground, and the CPU must contains only a single CPU there, and we are configuring packet pools also, and it uses the foreground CPU alias, and we have the number of packets and the number of cache packets also configured. The problem comes when we are going to have another CPU using this packet pool or another application instance, another thread, another process, whatever. And of course, if they are on different NUMA sockets, then we're having to pay the penalty. But if we change the configuration just by adding the type as NUMA instead of the default setting, which is the default, we're going to create two separate packet pools, and the given application instances are going to use the one on their own NUMA node.
So in this case, actually, I mean, it's our responsibility to create these packet pools based on the configuration if it's not clear. And so when our layer is initialized, if the application asks for allocating these packet pools in advance, then at our service startup, which we were talking about, touched yesterday, that we have a service. So at our service startup, we pass the config, we create these packet pools by calling the same RT create pool, packet pool or whatever function, and then we create these two pools. In this case, if it's a NUMA. So you just change the type to NUMA, and then instead of creating one, we just create two.
And so if we want to run multiple instances, then they are going to automatically attach to the appropriate packet pool.
So the application, when the application comes up, the client side, so when the application comes up, they just say that I want to attach to my packet pool FG, and all the instances, so all the CPUs, all the instances running on those CPUs will be attached to the appropriate packet pool, depending on where they are running. We already know their location, where they are running.
And if you want still more details, because we have the luxury of using separate packet pools per instances, then we can configure that either just changing the type from NUMA to exclusive, and it means that every single application instance will have its own packet pool.
And this is actually, I mean, this is just one example with a packet pool, but you can do this with different, anything else. Like in a MEM domain, if you just create an exclusive MEM domain, I will be talking about that later if we have time.
Example, yeah.
So then, for example, you can do the same with counters. So if you want to, you just create a counter pool, whatever, like similar to this packet pool, you create a counter pool, and then you can, just by changing the type, you can switch from using a single count where you need to use atomic counter increments, or if it works better for you, then you can just switch to per execution unit, so per instance packet pool, and in that case, or per CPU, yeah. So in that case, you don't have to use atomic increment. And then on the control part, the control plane, you can also connect to all of these instances. So the only thing the control plane does, it just fetches the number of these elements inside the pool, number of counter elements inside the pool. And if you only have a single one, then you will get back a single one. You don't have to aggregate. If you have multiple of these, then you aggregate on the control plane. But you can avoid, this way you can avoid atomic counter increments.
So on the fast pass, it doesn't hurt to use these counters. Our resource allocator is the very moment is static. So it means that before any application starts up, we run our own service. And this service is going to classify and arrange the resources. Basically what we can do is that when we have lots of different types of resources and resource pools based on some rules, we're just assigning. So we're assigning memory or memory areas to CPUs and interfaces together. So when an application instance comes up, a thread or a process, and requests its own resources, we're just passing them the appropriate ones. So we're trying to think that these are the most efficient resources they can get. Let's take an example where we have a native workstation with 4 sockets and memory interfaces. We're not mentioning here the storage, but we can add it. So basically, resource manager starts up and auto-detects basically all the resources we can handle. And auto-detect is important because if you don't have the information and we don't have the communication channel between the host and the guest, if you need it, of course, we can also run in native, then it means that we have a chance to sort of detect the environment. There are open source applications to detect even the cache sizes on different levels of the CPU, also verifying the memory, which memory is allocated in which NUMA socket, and all these things. Even we have a tiny program just to detect the HT pairs, HT siblings around something, and so based on that, we can have sort of an appropriate picture about the system. And it means that if you're fulfilling all the requirements, it means that at that very moment, our application or our environment is sort of DPDK confirmed. And actually, we have heard a problem that some customers or vendors cannot exactly tell if DPDK at all can run on their machines because of different problems with the resources or the resource types or even just the CPU type. And actually it can be pretty easy to add it, just a stamp that this environment or this machine is DPDK verified. But it of course requires to set up the appropriate requirements for that. In our case, resource manager can be anything, even a daemon, a binary, or a library. We use it as a daemon at the very beginning and also as a library during runtime. And what we do basically is reading the configuration, which we have seen the example before, and store it as the free resources. We use the extended attribute tree for that. It works pretty well for our requirements. What we are not yet ready with is supporting pop-up resources like pop-up CPU, memory, and interfaces. And when we have all the free resources, we can link them together in a pretty efficient way. What I was already telling that we can assign to an instance the appropriate and the fastest resources.
So we can, yeah.
And also, so we have a notion of mem domain, which means partitioning the memory and configuring it. We also have a packet domain, which means basically defining where the packets will go through the system and how will it go. It's a bit similar, or in many terms similar, to the IP pipeline configuration, and if we could mix them up together to merge them, then it could give us really a powerful configuration too.
And just on a packet domain yesterday, we discussed about this special type of POMO driver. So that's probably how we can move this implementation or the concept of this packet domain into DPDK. So it's like if we can create a new POMO driver type, like which is using RTE, ETHEF abstraction. So we have a new RTE POMO driver type, which is configurable. So for example, you can configure which packet pool you want to use on that for that POMO driver. So at the time of initializing the POMO driver, we can create the packet pools already and attach to the ports which you configure to attach to. So it's like you can just name the interface, the kernel interface which you want to use for DPDK. So when you initialize the POMO driver, it itself creates the packet pools, it attaches to the ports, and it can also have another way of abstraction, like we call it virtual port and virtual queues. It's like you create one port. So for example, if you, from the application's perspective, application only see a single port, and like a fabric port. In our case, we use that fabric front panel, and in that case, the fabric port is just set of queues. So like if you're running 16 instances, all these 16 instances want to attach to the fabric queue, to its own fabric queue. And in this case, if we can abstract what is behind that fabric port, depending on your platform or your configuration, the same port and the queues within that port could be mapped either to multiple VF devices or or multi-queue of Virtio. If you have multi-queue support, if you don't have, then you can have the queues could be mapped to software queues where you steer the packet or somehow distribute the packets across. So things like that you can abstract. So, but still, the application just tells that I want to fetch packets from my fabric queue, and then it can transparently map to another. So I mean, we can still use the existing POMO drivers. It's just that it's one abstraction. I mean, we still use the RT isDev, but then behind the RT isDev, there is another RT isDev which is not. I mean, we can make it performance efficient. So actually, what we are doing is caching on the function pointer on our layer, so we don't have to go through the RT isDev, and that also gives us a boost.
And there was the third domain, the DPDK Verification Domain, we introduced. Basically, this is our solution for function chaining. So we let the applications run next to each other, even within a single virtual machine, totally independent DPDK applications, because we have the environment that basically configuration files are in dedicated directories, and also the resources. A given DPDK application sees only the resources we pass them, the generic resource manager above the DPDK domain. So it means that even if we have in a virtual machine 10 vCPUs, we're just passing 4 of those to one application, so it thinks that he has only 4. We do separate all the resources.
In memory, and so the application within this pool can access only the memory which is assigned and which the application has the access to.
Here's a clicker. Your turn.
Okay, so I mean, now I'm going to talk about a bit more details about our memory management, which is again using this type of pool allocation. So most of our resources in this, what we are talking about is using this kind of pool and pool mechanism. Like you need to have, I mean, a port is just a pool of queues, or like the same for the memory partition. So we are dealing with memory partitions. So currently what we have, we showed this on the DPDK Summit, in our DPDK Summit presentation. So it's like what we have now with DPDK is that when you allocate memory, so we have 2 processes, or could be 2 threads as well, is using DPDK memory. When you call the RT malloc, everything now is in a simple single socket. So then that's what you get. You get fragmented memory. So you then have a separation of the memory used by the process 1 and process 2, which could be a problem if you, for example, if you want to support high availability. In our case, we need to support single process restart. So when a single process restarts, you should be able to clean up all the memory used by that particular instance, and then or you may need to reclaim the instance when the process comes back again, and we want to control that. So I mean, these are the memory management goals. What was our goals for our part of application is like we wanted to give them a simple memory management API and transparent NUMA awareness. So the application, most of the application doesn't have to be aware of the NUMA, because most of our applications are like the same type of instances.
Actually, we want them not to be NUMA aware.
Yeah, we want them not to be aware. In some cases, you cannot avoid that, but most of our applications is like that. Same type of application. Everyone just wants to attach to the fabric, front panel, whatever their ports, and everyone has their own, or want to have a private memory, and they are quite well separated. So we slice the traffic across these instances, and these instances are just processing a slice of a traffic, like flow pinning. The other instance doesn't have to know anything about the other processes session database. So in this case, we can give them transparent NUMA awareness by knowing their location. So we know where they are pinned to, and we know which NUMA socket they are running. And what we already described as part of the packet domain or to the packet pool example, they just attach to their own pool. And so yeah, so flexible configuration, reconfiguration, which allows applications to move in between platforms. So we don't want the application to be recompiled or rebuilt just because of they are running natively or running in a VM, running on top of a Zen or VMware. It's still the same application, still the same library. They just we just underneath take care of the resources. The application also has some responsibility in some cases because they have to, depending on the environment they are running, so they probably need to detect how much memory I have. So they, depending on that, they will apply a smaller footprint of like the supported users will be less in that environment.
Testing is a good
measurement of performance penalty due to that?
There's no platform.
That's the idea. So everything we do is with the resource management and allocating resources is background task. Basically, it's slow paths. So before starting anything, and on the packet processing path, on the fast path or foreground, we already have. We try to give the best available resources. So there is no overhead at all of our resource management. The benefit is that something like if you start up a VM 2 or 3 times, we have the very, very same performance because we most likely assign the very same resources. And without having our resource manager, we've seen pretty strange behavior that if you restart a VM, then you have different performance numbers from restart to restart.
And that's our main goal, that we want deterministic performance even in a virtualized environment. And so all the time, we don't want to rely on how the Linux underneath allocates memory or whatever other components. So that's the...
Testing is also a good example because at our company we have lots of different automated test systems. Some of those are based on VMware, we have VirtualBox implementation or whatever. And it means that with using our application layer, it means that applications can be tested even in a scaled down manner. It means that no change in the application code required. We just show to the application that, hey, instead of the 4 CPUs and the 4 interfaces, you have only 2, and they run with that one. And even we can mimic CPU. So even if in a virtual machine you have a single CPU, so on your notebook you want to test an 8 CPU system, you can do that. Of course, you shouldn't expect performance, but all the functionality will be there.
And by the way, that's a generic rule that on a forwarding, whatever you can do on a control plane, you do it on a control plane. So in the forwarding path, you don't want to check multiple times, am I running in this environment, and then I'm jumping there. And so you want these decisions to be made on a control plane, and then provide the database already available for the fast pass to make it more efficient to run. Even by swapping pointers, function pointers, whatever. Or
You need to speed up.
Yeah, yeah, we need to speed up. So yeah, memory partitioning is the main thing. So this way, we touched that also yesterday, that the application can request for partitions. Actually first I described this. What is a man domain? So a man domain is named and indexed memory partition. It's a shared memory with defined properties such as the location. So it's like we know the location which NUMA node it was created, size of that partition, if it's physically contiguous or not, and type can be different types of man domains. You can have huge page memory, MF5, inter-VM shared memory, distributed memory. So actually, from the application perspective, it's just virtual address. So I mean, mapped memory into the virtual address space of the application. So the application doesn't have to know anything about why running if I'm accessing an inter-VM shared memory or distributed memory. So that's our main goal, that the application, whenever, even on the control, even in their control plane, they will never tell, or they will never directly attach or want to directly attach to an inter-VM shared memory device. They just say, give me my pre-configured memory for my packet pools or whatever, or some private data or whatever, and then we will just give them or map it to the address space where they requested. Okay, man domain pool. So this is just like whatever we showed already. So it's like a pool of memory partitions with a name. So in our case, we predefine these three different types: the default, NUMA, and exclusive, as we already showed that in a packet pool configuration. So in the default, that could be even, I mean, we don't care memory, and the NUMA is what, in that case, you will create two different types, or actually depending on where the application instances are running. So it's like within the CPU set, if the application is only using a single NUMA socket, then you will only create a single NUMA partition, because you will never use the memory partition on the other socket.
Yeah, recently we've seen lots of applications that they run virtualized, and their solution for avoiding the QPI hit is just running on a single socket.
But this way they can really be NUMA aware, because I mean, we know their location and we know which is the best memory partition for them to run on. So it's like, it can be compared to a hard drive, like partitioning a hard drive, and then you store files, and this partitions files within. And usually, I mean, that's also something which is so coming up with this configuration, that's a system engineering task. So you need to think on your application model, what is best to your application, how can you solve these migrating in between these different environments. And if you do it right, then you really don't care, or you don't have to care about how you move. I mean, when you move your application, you can move to different platforms, so run the same application on different platforms. And yeah, we have a simple application API. Probably it's not more interesting here, because this is.
We just have our own implementation, because we wanted to make the non-DPDK user applications like easier for the migration. So we came up sort of a simplified API, but I think we will not discuss it right now.
Yeah, and actually we touched that briefly. It's the same thing. When application just refers to its partition by name, and then you will get whatever is configured. And yeah, so this is just configuration example where you have, I mean, we are dealing with the CPU aliases, but this could be an instance per instance. So you have an instance group where you group the same type of application instances together. And instances, it can be a thread or process as well. And then you describe the foreground CPU alias, which means that you want to filter out every second CPUs in this case. So you will be running on these the hyperthreads only if you have that layout. But if you have a different layout, you just change your CPU alias, and then you can get to the same. So you don't care about the underlying layer, because in some systems you may have this topology where the hyperthreads are on an even odd pair fashion, and also the socket can vary depending on how you are or how it is exposed to the application. So yeah, so this is just an example. This is the same thing what we already mentioned in a packet domain and a packet pool.
Different type of resources.
Yeah, so this is our configuration. This is one example. So here it's a default type. You specify where do you want to use this memory, and then alloc memzone true. That means that we will pre-allocate the memzone for that application, so they don't care, so they then have to call memzone alloc whatever. This can work for DPDK as well. So you can predefine memzones, so you don't have to create memzones in your when you're bringing up your system. You can just attach to it because you know that it's already created. So it can be something which could be moved or implemented inside DPDK. And now we're dealing with the size, but the size could also be, I mean, instead of the size, you can also mention that here, I mean, instead of mentioning the huge page sizes, you can mention I want to fastest memory. So if you don't want to show the application, that application doesn't have to know about the huge page sizes. So in this way, you can even migrate in between different architectures. Like you just say that for my application shared memory, I will be accessing it on my on a fast pass. So I want it to be the fastest memory. So giving the fastest memory.
How do we take the 1 gig pages? We should take it before the Linux.
Yeah, it's the same way today. I mean, what we're doing today is the same way. We're using the DPD the same way what DPDK does, collecting the huge pages. Actually, we're using the DPDK code for
course,
that. So
we still use the very same. So DPDK parses and classifies all the huge pages. So what we do is just group them to our needs, and exactly, and we release all the others. Get back to the system. It means that either we can start up our own next DPDK domain, which will see the free huge pages and allocate all those.
So it allows us to even classify the memory. I mean, we can pick the best huge pages. So if the application requests for 4 gigs of physically contiguous memory, then we can prioritize that request. So we can first allocate that 4 gig to make sure that it's physically contiguous, and then the rest may not care. I mean, the rest may be used only on a slow path, so you don't care. You can even use malloc for those. And that the man domain can allow that as well. So if you configure man domain where you don't care the performance, if you don't have huge pages, and if you don't care performance, and if you don't care physically contiguous, so if you don't have huge pages, it can just we can just use Raven.
Yeah, I heard the question as 1 gig pages have to be configured when you boot the kernel versus later. So I can't come along and say, oh, 1 gig, I'll put 2 of those on.
No,
So-
yeah.
That's the point. It's more of a static binding than dynamic. So
No, you can-
train.
Yeah, I mean, in this case, so we also have a dynamic API where we can, but we don't want the application to deal with these 1G huge pages. So that the best would be if the application would just, we would just define types for the applications, like 3 types. We are also using that. We have 3 types of memory where the application just says, I want to allocate the fastest memory, or I want so it's like fast, medium, and slow. So in that case, you can prioritize. For the fast pass, you will always allocate from the fast pass, for the fast memory. And if you have the option, if you have 1G huge pages, you can even give them 0 TLB missed memory for every instance for this fast memory.
No,
Because
I
we,
understand that.
yeah,
It's
yeah,
just
yeah,
binding
right.
when you define.
But there could be, I mean, if we can build this memory management into DPDK, we can have other ways of allocating memory. So it allows us also to, so like yesterday I was thinking about a QEMU driver, a device, a new device. I don't know if it would be possible, but develop a new device, or maybe using the IVSH MEM device just to request for memory. So you just boot up the kernel with small memory, with the kernel, whatever is required for the kernel, and then you use the IVSH MEM device or another device to request for more memory. And then if you can map that, if you request for physically contiguous memory, and if you want that to be a 1G huge page, you can use the kernel if you have a kernel driver, or even with mmap, I guess we can map today physical memory. Can be mapped as 1G, 2M, or 4K. So you can use the mmap. I guess it's there since 3.8 kernel, which is again another way of allocating memory. So if you don't want to deal with 1G, 2MB huge pages, you just allocate 1G huge pages and then remap them as 2MB or 4K. And you have a different.
Recently, we were supporting a project where a specific NPU behavior was sort of ported to x86, and our layer was their supported layer. And that specific NPU had different types, physically different types of memory. It's a bit similar to the Skylink's new embedded memory. So even on x86, if we had an API to command Skylink how to use that embedded memory, we could really make useful for forwarding tasks.
Yeah, or if you have a scratchpad in certain network processing, like in our ASICs, we have a scratchpad, which is unique per execution unit. So in that case, you can just create a man domain where you want that scratchpad, and that's the fastest memory, and that's the fastest available memory. It's like a register. So then you can use that memory, and applications can allocate from that memory. So we can just, even with RTmalloc, they could allocate from that memory. I'm thinking of running on a different architecture, so building DPDK on ASIC or different architectures where you have different types of memory. So yeah, so I mean, this is our simplified API. So application will, and I mean, that's the main thing, that application, the client doesn't have to know anything about where it is running in most of the cases. So it's like they just want to attach to, just refer by name, and then we know which memory is the best for them. So yeah, this is one example. I mean, this is another example of the NUMA type. So the NUMA type, it's like you just change the type to NUMA, and you say that I want this to be per NUMA. So it will allocate 1G per NUMA, 1G partitions or 1G partitions per NUMA. Actually, you can even do something like you put 1G on 2 meg, 1G on 1G, and then application gets 2 meg. And because this is at the end, it's just one MEM zone, so we are allocating a MEM zone out of that. And yeah, so it's application when an instance tells that please give me my referred by name, my app NUMA share, then depending on where the instance is running, they just attach to the right NUMA. And on the control plane, if you, for example, if these are the pip tables which you want to maintain, and which you want to replicate, then on a control plane, the control plane can attach to both partitions. It just have to request the number of partitions within that pool. So you can, that's another API, give you the number of indexes, number of partitions inside this NUMA shell, and then you just have a for cycle, and then you attach to both partitions, and the control plane can replicate. Yeah, okay, so this is, and the same thing for exclusive. They just change it to exclusive and attach everything. Everyone will attach to their partition. And actually, this is a model which is useful when you have completely separated. So every instance is doing the same thing, as I described, like receiving packet, processing packet, and then sending out packets. And there is no communication in between these instances, or that communication is always through the control plane, whatever. In that case, these memory partitions can fully be isolated, which gives us memory protection as well, because what we are doing in this case, if these are different processes, then this memory partition will not even be mapped into the instance 2's memory space.
So that also helps when we need to generate core dumps, because basically we save lots of time. In one of our environments, we basically use 96G of memory, and in the original versions, when we had to do a core because we didn't have any other opportunity to debug the issue, then actually it ate up all our resources, so both the hard disks and lots of time. But if we can map only just a few huge pages the given process really uses, then the generation of the core file is much more faster.
And this is, if you think of this, this gives another option of mapping the partition into the exact same virtual address space. If these are multiple different processes, you can map within this instance, you can map this partition into the same virtual address space. So we have the per instance memory in this case. So which could be very useful. You don't need to use the thread locale, so you back up the thread locales with this type of memory, and then you can, if this memory is a 0 TWs memory, it's just you can even have, if it is configured, if the virtual address is configured in the man domain configuration, then you can even hard code that address, and in that case it's just a constant. And so yeah. Yeah, I think we have an advanced man config API. I mean, this is something which allows the applications to allocate. So it's not through the configuration, they can just allocate it similar to what we have the DPDK man zones. It just allows the application to attach to mem domains, and which means mapping into the virtual address space. It allows them to map it as read-only, because that gives the other option. Only the control plane part has read-write access to that partition, and the application instances can attach to as read-only. Or, and in case of a FIP table, maybe the FIP table is not even inside that VM, it's an inter-VM shared memory managed by another VM. Yeah, okay, so just keep these, I guess, times out.
This is the outcome.
So yes, this is the outcome at the end. So we have, so if you have these two processes, like instead of this fragmented memory, you will get a clean memory partition. So this in DPDK, if you want to build it into DPDK, so at the moment we are using the DPDK socket. So for us, when you're running the application in a dual socket system, if you check the DPDK dump config, you will see 16 or more sockets. That's how we manage the sockets. But it could be done in a way to, if we would introduce RT malloc types, or because now it's on a heap. I mean, with the latest changes, we have a heap. So if that heap could be per application instance, and maybe it could be configurable via these methods, then we can achieve this even in a DPDK application. So, and we have per Alcor, we can store what is the heap for that application instance, and then in that case we can achieve the same thing with the DPDK application. So it's like, and then this is, so for us multiprocess, because of high availability, is important, because if you kill this process, you can just clean up the memory, and then you're done. Or you just, if you want the application to reclaim, they can reclaim the same memory. But this gives protection, and also TLB, which we showed on last year. Like it can help TLB, because if you are only using 4 1G pages, then you will have a 0 TLB miss. While in the mixed mode, you will be using 8 pages, and then you have the penalty of TLB misses, which could be huge in a VM environment. Okay, so future ideas.
Yeah, hopefully some of those could be done later. One idea is to support non-DPDK applications without using the API itself. So it's just like an idea, something like using an LD preload to replace some of the portions to make them faster.
One of our applications actually using that to overload the malloc function, and then malloc will be using our memory allocation. So by using the malloc, whatever, so you can just speed up the application this way without changing any code in the application. You give a 0 TLB miss for these instances.
Yeah, this is what we were talking about. So basically, we could define even faster or slower memory types if it helps. Or basically, we have a sort of a chunk allocator, because with supporting a 32-bit project, we also require to have much smaller chunks of memory. So we didn't want to keep the original 11 or 16 meg heap. We had to go down. And right now, it is possible with a chunk allocator to allocate 32 bytes of memory, of just tiny chunks. And what we did is RT malloc is replaced. I mean, the implementation of RT malloc has just one more branch based on the size the application wants to allocate. We're using the original DPDK malloc, or we go with our
yeah, actually we hijack the socket inside the RT malloc. We hijack the socket type, we overload the socket type, so that can be used as, so in the lower part you can refer to the socket, and that's something which how we can build this into DPDK. So like, if you want to allocate memory in the same traditional way, you just use the socket 0, socket 1 if you're running on a dual socket system, and otherwise you can also specify the type, and in that case you may be using a different memory, and maybe if it's the first time you are accessing that, then it is also mapped into the virtual address space, and so this way we can improve a lot.
Yeah, the DPDK certification we were already talking about, either for just virtual machines or configurations or hardware. We have heard from lots of people that basically assembling the whole configuration line to start a DPDK application is a pain. So probably we could have a GUI, just like many VMs or any other applications have just a front end. Probably it already exists, so somebody might have already implemented. And developing this idea further, we might have visual resource allocators. So it means that probably just an application could be clicked. So if you have all the resources like CPUs, interfaces, you're connecting them, pressing enter, and you're done. You basically have the configuration. Either can be sent to our resource manager or can feed the DPDK with the command line, if the command line is detailed enough to handle all these applications.
Or thinking about an SDK where you have all these supports.
DPDK OS or a DPDK distro, it looks like DPDK has its own pretty well-defined requirements if we stick on the performance side, and probably just to make other customers or applications come to DPDK, it might be pretty handy if you just release an OS or even a VM image where everything is pre-configured. He just needs to start it up and he can enjoy.
So right now the problem is that we have these different types of hosts, and the customers want to use their own host environment where we don't have, I mean, it's hard for us to isolate everything, isolate the CPUs, and I think it's a problem for everyone that you need to isolate, you need to guarantee the performance, and by the way, that's something I guess which we are missing is or I haven't seen that in the dpdk.org, that the requirements which we need to run high performance, I don't know, we may have that somewhere, but this would be good to have a list where you specify that you need, if you want the highest performance, you need to isolate your CPUs, isolate the memories, and then if you have that list, so that could be part of the DPDK certification also, like you need all these on the host side. I guess that this is something which the probably OpenIFV or the OpenStack, the isolation components are already working on, but it would be good to list all these things which are required to have high performance.
There is a patch gone in just in this release with a new part of the documentation about how to get best performance from DPDK. It's a start document really, you know, how to isolate cores, etc. So yeah, this could probably be improved. And
yeah. It's like showing all the options. I mean, how ISO CPUs or what are the ways, or CPU sets or whatever, which are the current options today to fully isolate RC no callbacks, what are the required config setup configuration and things like that. So just get rid of all the context switching overheads and everything on a fast pass core. And memory wise also, which I guess we have the requirements, the huge page packing and things like that.
Regarding the high availability, the idea is that if you have an application which runs, for instance, eight processes, we could have a standby one, which means that, as we already said in our case, all the 8 processes are pretty much similar. They do the very same. They are just run to completion model. So it means that if one of those crashes, we don't really want to even wait for them to do the core dump if we enable it and restart it and whatever, but we might have a standby instance, which means that immediately can take over any of the failed instances job. Of course, it needs some more resources allocated, but it means that 999 can be a bit more easier achieved.
Yeah, this is what I was already talking about, so I don't know if it's possible or we can improve. We should improve, as we discussed yesterday, if we should improve the IVSH memory, but this could be one way to get. So for example, if you have a DPDK device given us, like EMU or whatever, I don't know how, if it would be possible, we can just send down requests and maybe request for the topology, the real topology. You want to know which CPU is mapped to where, which CPU is on which real circuit, the mapping on the other side if you want to know how memory is mapped. Yes.
How can we test these ideas, because none of the things you presented before are available on DPDK, so how can we make the links as the contributors to DPDK?
Yeah, that's a good question.
Our company is not really good at the moment of open sourcing things. They're working on that, so we already have some projects globally in the Ericsson. And actually we got a promise this year again that we're going to have the possibility of uploading some of these things. It's just, most of you must know that in a bigger company the things happen much slower and the decision making is unbelievable.
And there is also that we started these things to be built on something on top of DPDK. So our code is not in DPDK style. So if we want to upload, we need to find a way how we can fit these blocks into DPDK. That's why we are thinking in like improving the memory management part by introducing a new type in RT-malloc. But that is, so we can probably keep some part of our code, but we almost have to rewrite that code to be DPDK compliant.
But all we can say, it does work because we had all the measurements, so that's why we try to explain the idea.
And the other problem is, of course, the resources. I mean, we are allocated in multiple projects, so we cannot. And it's hard for a company to say that okay, we want to open source this, and then they will allocate our times just to deal with open sourcing. So these are there are these problems which we are discussing right now. Can we really contribute to DPDK?
Actually, yesterday it already popped up that following the DPDK.org mailing is even sort of a full-time job because there are so many mails and ideas and implementation solutions coming that if you really want to understand what is this whole given trend about, then you need to do your own homework to dig the code. And there are 2, 3, 4, 10 ideas a day or things. Oh yeah, a startup. So here we have all the guys good at DPDK, so probably it could be good. Not for us, of course we cannot, but a startup might be nice. Thank you.